Welcome back, folks. This is the last of 4 videos where we're looking at first-order transient responses of some what might seem like simplistic circuits, but they are very informative into the form of the solution, and we're trying to get that form. Guess what? The answer to this one is going to follow the form of the last 3 videos, and then I'm going to sum that up in the next one. Okay? So we just discharged an inductor, and if we're going to discharge an inductor, we got to figure out some way to charge it, right? So let's do that. Here's our inductor, and we've got a voltage supply over here. I went with a generic voltage supply on this one rather than a battery. It doesn't matter as long as there's a voltage differential. We're connected to the resistor and the inductor over here. So now we have this additional component, and that's going to change the equation a little bit. Okay, so let's get the color I want. Okay, we are going to use mesh analysis again. We have the time domain expression for the current flowing through the inductor. That's really what's of interest to us. Outside of that, we're going to perform mesh like we have been doing all semester. So we go up Vs, we go down R times IL. I'm going to drop the functional notation, and I go down L di dt. Okay, and there's our differential equation, and it's first order. We have the highest order derivative that we have is the first derivative, so it's a first order differential equation. What we're trying to find is the time domain expression I sub L that we can plug in here and have this equation be true. Once again, we're going to separate and integrate in order to do that. Okay, so I made my substitutions. I went a little faster on that one. I hope you forgive me. And we're going to try to get this. We're going to try to handle this R, and it's going to end up looking a little different this time, only because we have this constant Vs here. We don't have a constant current we're charging to. Maybe that would be a simpler thing to work with, but here we are. I want to get that R off of that term, and I'm going to move it over here and over here by dividing both sides by R, right? So this is going to be Vs over R minus I sub L, because it's going to disappear out of that one, and then I have minus L over R. Okay, well, there's L over R again, and I said those were going to stay together for these inductor equations. Okay, equals 0. Playing the same game. We're trying to get all of the ILs on the left side and all of the T's on the right side. So we're going to pull some stuff over to the right-hand side. I'm going to pull I sub L over, and I'm going to pull Vs over R. So it's not a current. Well, it is a current. Look at it closely. It is a current. It's a voltage over resistance, and those are both constants. So it ends up being a constant current, even though it's in this fractional form. It's really just Ohm's law rewritten. I'm going to pull IL over. So let me get this term over here on the left side, since that's going to stay. IL is going to move over and become positive IL. And Vs over R is going to move over, and that's going to be negative. Okay, so that gets us part of the way there. Bring in... what do we got to do here? We got to bring L over R down. Okay. And we're going to get IL minus Vs over R. And we're going to bring L over R down that way. And then I'm going to swap, I'm going to swap out this. Okay, I'm going to bring that down, and I'm going to bring this up. And that should get me... I think that gets me to the point where I can begin to integrate. Let's do it and see what happens. DIL over IL minus Vs over R. Okay, so I divided both sides by that. I'm going to multiply both sides by dt. Okay. Hold on 1 second. I've got to track down a negative sign. I want to make sure I'm doing this right for you the first time. I found it. I dropped a negative sign. I knew it was supposed to be there, so when I got down here, I was looking for it. Look at that. I lost that negative sign. Okay, and let's see, that negative sign should have ended up, we could have moved it at some point. It ended up there, and it ended up there. Ooh! Dropping a negative sign is like dropping, well, it's like dropping a negative sign. We'll leave it at that. Okay. It's the opposite answer, right? I couldn't have been more wrong if I had continued with the analysis that way. All right, mischief managed. Let's see where we go from here. Am I good to integrate? I believe I am. Come on, integrate for me. There we go. So we integrate from the initial condition up to some time t, right? And we integrate from t equals 0 to t equals t. And we just swap out our variable of integration there. Okay, these of course are functions of tau now. All right. So performing those integrals, we've done this a few times now. So there shouldn't be anything tricky here. We got a natural log of I sub L of tau minus Vs over R, and we're going to evaluate that from I sub L of 0 to I sub L of t. Okay, that's the left-hand side. Over here we have negative tau over L over R, and we're evaluating that from 0 to t. Should look awfully familiar. We just have a couple different variables in different places. Let's see, log of IL of t minus Vs over R. All of that, let's stick that in some parens there, all of that minus the log of IL of 0 minus Vs over R. Right-hand side, negative t over L over R minus 0, oh, it ends up being a plus, 0 over L over R. Okay, that's going to cancel, so I'm going to start to ignore it. Using that log property, just abusing that log property. IL of t minus Vs over R, all of that over IL of 0 minus Vs over R. Okay, and that's all equal to negative t over L over R. Getting rid of that natural log because we want this one right there. We want that by itself. We're going to make both of these nice capital. That's not capital. Lowercase e. I was thinking of the big E. I was going to make a big E joke, and then I was like, well, you know, anybody watching this outside of New England, so even southern New England, isn't really going to follow that. Okay, so that drops out. Go look up the big E. There's no big E this year, I think. Different big E than what you see there. Okay, so we're left with this fraction over here, and we have e to the negative t over L over R. I want to move this into the numerator, so I'm going to multiply both sides by this, and that's going to get us awfully close to our final form. Okay, I'm going to keep this in brackets, IL of 0, which is our initial condition, minus Vs over R, which is kind of interesting in its own way. And we'll play with that as we begin to analyze circuits using this stuff. Okay, and we got that natural exponent over there. All we've got to do, we want this term by itself. We just have to add this one to both sides. So we're there, okay? Last step, here it is, Vs over R plus IL of 0 minus Vs over R e to the negative t over L over R. Whew. Pay close attention. Well, first off, that looks like a charging capacitor, but we've swapped out the capacitor voltage for the inductor current. Looks pretty similar. And if we're paying close attention, it looks like the other three equations all together. And that's what we're going to talk about in the next video. How do we generalize this? And once we generalize it, then we can move on in future videos and say, okay, how do we exploit some things about the circuit in a way that allows us to fill in some of these values without doing any calculus or differential equations. We just want to use the circuit analysis that we know, we've grown to love it, and we're experts at it. Hopefully you're feeling more comfortable just performing circuit analysis. So we're going to figure out how to leverage that knowledge and write expressions like this that are correct. Okay, summing it up in the next video. I know you're waiting for that. Everybody was waiting for that. Stay tuned and good luck.